Okay, so today we are looking at integral defined functions and properties of integrals. So the AP exam loves to give you what are called integral defined functions, which is a function that has a definite integral in it. A definite integral is an integral that has limits here, and if they give this to you as a function, then one of those limits, and unless they're really giving you a curveball, it's going to be the top one, is variable. All right. Notice here, you notice this probably on last night's homework as well. If this variable is x, that should match what's here. Right? These two match. And then these two right here, they match each other, but they have to be different. Right? So this is the function that you are integrating, and this is the variable that's getting plugged in. It has to match whatever variable you have here. This variable is a lot of times it's just like a dummy sort of variable. X is what you really want there, but whenever you take a derivative of this, like we were doing last night, then you end up having to plug that x in there for that. Capital F of x finds the area under the curve of lowercase f here. Often, not always, but often they'll use a capital F for the integral defined function, and then they'll have the lowercase of that letter as the function here. So if I have an integral defined function, right, and I want to find the derivative of that function there, so if I want to find f, capital F prime of x, that means I'd be taking the derivative of the integral of from a to x of f of t dt, and this is what we learned last night. What happens when you take the derivative of the integral? They more or less cancel out, right? You are just taking whatever your top limit is, you're plugging it in right here. In this particular case, you're just going to get f of x. So to take the derivative of this integral defined function, you just get the function that's on the inside. And I have my little picture over here. I thought I saw this on a t-shirt a while back, and I need it for fundamental theorem of calculus this time, but I can't. This isn't even a good picture of it. I couldn't even get like the good quality picture, but so like what's happening here is like our capital F is like our Batman, right? If you take the derivative of Batman, then you get, why have I forgotten the name of Batman? What's Batman's name? Bruce Wayne. You get Bruce Wayne here. But if you integrate Bruce Wayne, then you get back to Batman, right? These are inverses of each other. It's just, that extension of the fundamental theorem of calculus. So what we're going to see with integral defined functions is they're going to ask us a lot of the questions that they used to ask us about like f prime, and f double prime. And they're just going to let that f be this integral defined function. Okay, that adds another layer to it. So we'll see what some of the questions look like here. So here's an example. Let lowercase f be the function given by f of x equals the integral from -2 to x of g of t dt, where g is a differentiable function. The table above gives selected values for f, g, and g prime. If h is the function given by h of x equals 2x plus sine x, for what value of x is h of x equal to f prime of 2. Got a lot of stuff going on here. You've got f's, you've got g's, you've got h's. It's really hard to keep everything straight here. But if you look at the end, that's where it's giving you the question that you're being asked. And we're looking for where h of x equals f prime of 2. Well, I know what h of x is, right? F prime of 2 is what I'm going to have to find, and then I'm looking for where those two things are equal to each other. So, f of x is the integral from -2 to x of g of t dt. But the question doesn't need me to find f of anything. I need to find f prime of x. What is the derivative of f of x going to be? Derivative of f of x going to be? It's just g of x. Right? Because if I take the derivative of that integral, that's what we were doing last night. The derivative and the integral just cancel each other out. You are taking that x, you're plugging it in right here. You are multiplying by the derivative of that x, but in this particular case, that's just 1. Right? So, f prime of x equals g of x. So when they ask me to find f prime of 2, it's really just the same as g of 2. And g of 2 can just be read off of the table, right? So when your x coordinate is 2, that's right here. We're looking at g of x, so that's -2. Now, this part doesn't have to be calculator active. It's this next part that makes this a calculator active problem. You're looking for where h of x, which is 2x plus sine x, equals f prime of 2, which we just found was -2. And I am not aware of a way to solve that by hand. This is a calculator active problem. So you would just pull up Desmos. And how do we solve this if we got 2x plus sine x equals -2? What do we do in Desmos? Well, I'm going to call it h of x since it is h of x. H of x equals 2x plus sine x, and then g of x or y equals, or anything, f of x, whatever you want to call it, equals -2. Right? We just put those two things in there, left side, right side. We're just looking for where they cross. We're getting -0.684. So A is going to be our answer. I feel like that I understand why we need to be able to do these types of problems. They could have just told us that g is the derivative of f right here, right? And then we wouldn't have like all these complicated looking integrals and things like that, but they're not going to do that. It's going to look like this. And they love to give these because it tests whether or not you have that knowledge of integrals and derivatives being the inverses of each other here. But most of the time, it's a very simple, like, oh, I'm taking the derivative of the integral, so I just get what's left on the inside for those. Here's another one, similar problem. Okay, the figure to the left shows the graph of the differentiable function g and the line tangent to the graph of g at the point 3, 4. So you have to be very careful in these problems. Make sure you're keeping straight what is f, what is g. This is the graph of g over here. F is the integral defined function. F of x equals the integral from 0 to x of g of t dt. Let h be the function, and then they give us this h prime right here. If the line tangent to the graph of h at x equals a is parallel to the line tangent to the graph of f at x equals 3, what is the value of A? So if we read that last sentence again, the line tangent to the graph of H at x equals A. How could I write that like in symbols for what I'm looking for? That would be line tangent to the graph tells me I'm dealing with a derivative, right? So H prime of whatever value A is right there is parallel to, what do we know about parallel lines? They have the same slope. So whatever I get right here for this slope of this tangent line is going to equal this next expression right here. And the line tangent to the graph of F at x equals 3. How could I write that in a much shorter expression? F prime of 3. So much like the last problem, I've got to find f prime of 3 first, and then I can use my calculator to help me solve here for the rest of that. So what is really easy to do is to treat f and g like they're the same thing. And in fact, they've given you extra information that you don't need here about g to try to trick you into doing that. But f is not this graph over here. F is the integral from 0 to x of g of t dt. We need f prime of x. What is f prime of x? This is g of x. So if I'm trying to find f prime of 3, that is just g of 3. What is g of 3? It is 4. Okay? Because you're just reading off the coordinates of this point. They gave you the tangent line there. They're wanting you to say that that equals 1/2, right? The slope of this line right here is 1/2. But we're not falling for it. We just need the value of g at 3. So we get 4. So we are looking for where h prime of x, which is x e to the cosine x, equals 4. And this is where we go. This is where you have to have the calculator. I'm not aware of how to solve this one either without a calculator. So you would just go up here and say x e to the cosine x, and then down here 4. Let me make sure I am in radian mode. Yeah. And so there's more than one answer, but they told us only to look from 0 to 7. So this answer here is going to be our correct answer, 4.577. Excuse me. Okay, questions there? Okay, let's look at 3 here. Pump allows water to flow into a tank at the rate of R of t equals 3t liters per minute, where t is the time in minutes since the pump was turned on. Which of the following defines a function that measures the accumulation of water in the tank during the time period from t equals 1 to t equals x, as the variable x moves along the t-axis as shown in the figure above? So what is graphed right here? They don't make it very plain, but what is graphed right there? What about the tank? Is it the amount of water in the tank, or is it the rate that it's changing? What? It's the rate. There's a few ways I can know. First of all, they do put an R of t up here. Second, this is 3t, which is just a straight line with a slope of 3. So this is the graph of 3t, right? So this is R of t. This is the rate. So this would be in minutes right here, and this would be in liters per minute. And so let's think about what they're wanting us to have. Which of the following defines a function that measures the accumulation of water in the tank during the time period? So accumulation of water is just our amount of water, like the amount of water, or the change in the amount of water, I should say, right? Not the total amount necessarily, because there could have already been some water in the tank before we started observing, but the change in the amount of water. So if I want just amount of water, then would it make sense to have 3x right here? That would be the rate. So that is not our answer. And B is also not going to be the answer, because to find an amount of water, we're going to have to integrate this situation, because we need to be doing liters per minute times minutes, right? Like finding the area here. Minutes cancel, just giving us liters. So we need to integrate. And C and D are very similar. Which one's going to be the correct answer? It's going to be D. How do we know it's D instead of C? 1 to x instead of 0 to x. So D is going to be the answer. Now obviously here, like, we're kind of trending towards having that answer that is an integral, but sometimes, whenever we get to the end of this class, they might be asking you the other question about the rate, and you have to be careful which one you're looking for. All right, so let's look at some properties of integrals that we need to know. And these will help us solve a lot of different types of problems. So I've got, if f is defined at x equals a, then the integral from a to a of f of x dx is going to equal. Now, an integral gives me area under the curve, right? So what is the area under the curve from a to a going to be? Or if you want to put a number in instead of a, from 1 to 1, or from 4 to 4. It's going to be 0, because what's the width of that interval? 0, right? So, like, doesn't matter what the height of it is, you get nothing. So if you ever have an integral where the limits here on the integral are equal to each other, it does not matter what in the world that function is, as long as it's defined. If it's undefined, like if it's an asymptote or something, then they really shouldn't be asking you that question anyway. You're just going to get 0. Okay? If f is integrable from a to b, then the integral from a to b of f of x is going to equal negative integral from b to a of f of x dx. If we are doing a problem from a graph, and we are looking at area like above the curve or below the curve, if you think about that warm-up that we were looking at here, let's flip over to this warm-up. If I had asked you to find me the integral from 1 to 4 of f prime of x dx, then the answer would be -7. Okay, so now if I switch it, if I make this 4 to 1, f prime of x dx, then I would get +7. The fact that the area above the curve is positive and the areas below the curve count as negative only works if you have like your lowest to highest interval right here. If those intervals are backwards, you go from highest to lowest, it's going to flip that sign, right? So we'll see some of that come up. All right. This one is just one that makes pretty good sense. Kids do fine with this one. If f is integrable on the three closed intervals determined by a, b, and c, where a is less than b is less than c. That means b is somewhere between a and c. If I find the integral from a to b, and then I find the integral from b to c, and I add those together, it's just going to give me the integral from a to c of f of x dx. This is common sense, really, when you start looking at like areas under the curves. You guys really already did that on the warm-up because you took those different areas and you added them together, right? You took those little pieces and added them together. Okay here? All right, if we have to integrate two separate functions, we can break them apart. So we could do the integral from a to b of f of x dx plus the integral from a to b of g of x dx. This rule also holds true. We really could put a plus or a minus there if we want. That rule is going to hold true for negatives as well. This rule does not apply for multiplying or dividing. So if you have f of x times g of x, you cannot just integrate those two things separately. However, if you do have some multiplication where this k right here is just a constant, so it's just a number, then you can pull it out front and it's going to be k times whatever the integral from a to b of f of x dx is here. So you can break it apart when it's just a constant. And then our last one is what we do if we have just a constant number. I almost think it's a little easier to think of this example with numbers put in there. So like let's say we're integrating from 1 to 4, 5 dx. If you think about the graph for this, the graph is just y equals 5, which is a horizontal line at 5. And we want the area under the curve from 1 to 4. 1, 2, 3, 4, 5, 6. So from 1 over here to 4. Right, so like if I graph that out, that's a very easy area to find because I'm just looking at a rectangle. What's the height of that rectangle? 5. What's the width of that rectangle? 3. So I would be doing 5 times 3, and I would get 15 for that. So let's generalize that for just any number, right? If I have a constant right here, like the 5, that's just the height of your line, right? So you're going to take k, and you're going to multiply. The width of your rectangle is going to be b minus a, right? The difference between your limits, how far those limits are apart. Right, good here? Okay, so let's look at some examples. And for this example, I have also given this to you as an integral defined function. Okay, I don't necessarily have to. In fact, in the original notes I had for this, this was not given as an integral defined function. But we've got this graph here. And we are told that g of x equals the integral from -1 to x of f of t dt. Notice this graph is f, not G, right? G is going to be the area underneath F from -1 to whatever value we're plugging in. So, if I want to find G of 3, G of 3 works like any other function, like for function notation. You're replacing the x with 3. So, we're doing the integral from -1 to 3. We're replacing that x with 3 of f of t dt. This just means the area underneath the curve from -1 to 3. So we're looking at this area here. Right. What shape have we got there? Trapezoid. So we're going to have height times average of the bases. Now, this trapezoid's normal. Like, it's not sideways like our trapezoidal rule. What's the height of that trapezoid? It's 2. And then my bases, the bottom one is 4. And the top one is just 1 divided by 2. And that is just going to give us 5. So G of 3 would equal 5. Now, questions there? If I'm asked to find G of 7, then G of 7, you're just plugging 7 in for that x. It's the integral from -1 to 7 of f of t dt. Now, -1 all the way over to 7 includes what we just found, right? So what I would think of here, you don't necessarily have to write it, but you definitely want to think it. I would think this is really the integral from -1 to 3 of f of t dt plus the integral from 3 to 7 of f of t dt, right? That's one of those properties that we just wrote down, right? If I have these integrals of these two sections that are right beside of each other, I can just add them together to get the full integral. Well, we just found that integral from -1 to 3, that was 5. And then I need the area of this part right here. Now, what do you notice about that shape right there? It's the same shape as the red one, just flipped upside down, right? Well, it kind of reflected over. You can do the full work for it if you want. The height of that trapezoid is 2. You're going to have the top base is 4, the bottom base is 1. We divide that by 2. But since this is below the x-axis, what do I have to do? It's going to be negative right there. So whenever I complete that, I will get 5 minus 5 and just get 0 for that value. So note, if you have like a positive area and a negative area that balance each other out, then you can end up with just 0 for this value. Did I show you guys that meme the other day about your average velocity? About being born and dying in the same hospital? If you are born and you die in the same hospital, then your average velocity for your entire life is 0. Because, like, it would be, you know, like all of your positive movements, or if you end up at the same spot, you would be, your average velocity is 0 for your whole life. And, you know, I mean, that could happen. If you live in the same place your whole life, you could very well be born and die in the same hospital. Not everybody dies in the hospital, but some people do. So, it's not totally uncommon, I'm sure. That's the sort of thing that the Instagram Reels gives me. Knows what I like. Hunter sometimes he'll get my phone, especially I put a limit on his because otherwise he might spend like 6 hours on Instagram at a time. And so if I'm out of time, every once in a while he'll have my phone and be like, "Do not be messing up my Reels. I'm gonna get dumb stuff that I don't want to see. I need my math videos and funny jokes about things, not whatever stupid thing you're interested in there." I sent him one video in the short little quarter zip phase there. I sent him one video about a quarter zip because he'd been talking about it so much. And I got quarter zip videos every other video for like a week on that. So now I have to be careful what I send to him too. I send him things I think is funny. All right, let's do this last one. We got g of -3. Now, be careful with this one. G of -3 is going to be the integral from -1 to -3 of f of t dt. And it feels like that's the area under the curve right here. Right? But when you're looking at the graph, you're always going left to right. So this area is the integral from -3 to -1 of f of t dt, which because it's below the x-axis would be negative, and you'd have 1/2 times the height of that triangle, which is 1, times the base of that triangle, which is 2, and you'll just get -1. So whatever you're doing from the graph, the area of that being below the graph being negative is assuming you're going from left to right. But do the limits on this one go from left to right? They do not. They're going backwards, right? Sometimes it's hard to catch on the negatives too because it still feels kind of like -1 is smaller than -3, but it's not. So what we want to do here is I always just like to flip my limits back around. So I would flip this and make it -3 to -1 of f of t dt, but if I flip the limits, it changes the sign. Right, so it's going to make it negative there. And so the integral from -3 to -1 of f of t dt is -1, but where I flip the limits, I'm going to get +1 as the answer. That messes kids up a lot because it's just so easy to overlook that, to not pay attention to the fact that those limits are showing up backwards. Another way to think of it is like this right here. X equals -1 is sort of like your starting point that you know. So if you're going forward, anything above is positive, anything below is negative. But if you go backwards, that switches, right? So if you're going from -1 backwards to -3, anything below the x-axis becomes positive, anything above becomes negative for that. So these will be some different things that you're expected to be able to do, types of questions that you'll see. You'll also see, these are probably more likely to be on the multiple choice section than the free response section. You'll also see some of these where they give you this sort of like generic function that you don't know anything about, but they give you pieces of information. All right? So here we've got the integral from -5 to 1 of g of x equals 8, and the integral from 1 to 5 of g of x dx equals -2. So if they ask me for the integral from -5 to 5, what would I have to do here? Just add these two together because they connect right here at +1, right? So I could just add these two together. So I would have 8 plus -2, and I would get 6. So like your homework's going to have sort of more questions than we normally have on homework because usually we only have, 6, 7, 8 questions. There's more, but a lot of them are super quick, like this right here for this. What about if we have the integral from 1 to 5 of g of x plus 5? I got a plus sign here. Those properties of integrals told me I could split that up, right? So that means I could make this, the integral from 1 to 5 of g of x dx plus the integral from 1 to 5 of just the 5 dx. So the integral from 1 to 5 of g of x dx is -2. That was given to me up here. Now, the integral of a constant. Remember, it helps me so much to think about what the graph looks like for that. We just have a 5 here. That's a horizontal line at y equals 5. We want the area underneath that curve from 1 over to 5. What's the height of that rectangle? That would be 5 because you got y equals 5 here, right? What's the width of that rectangle? 4, because we're going from 1 to 5, right? So we're going to get 5 times, I'm gonna write it out like this, 5 times 5 minus 1 is where that's coming from. So it's this constant times the width of the interval. But of course that just gives you 20. So we'll get 18 for that one. Nine is a little bit easier to do. You just have a coefficient right here. That just can be like pulled out, right? So this is the same as 3 integral from 1 to 5 of g of x dx. And they told us that the integral from 1 to 5 of g of x dx is -2. So we'll get -6 for that one. All right, let's see. Trying to make sure we get all the most important things done here. Okay, we need to do this one. All right, so this graph is given. It consists of 3 line segments and 2 semicircles, as shown in the figure below. What is the value of the integral from -4 to 7 of f of x dx? So in this case, this is in the properties of integrals section because you're basically breaking it into little pieces, right? This just tells me area underneath f of x between -4 and 7. So that looks like here, let me use a color instead of black. Let me use green for the top part. So we're looking at, this area up here. I'm going to break it. I would do this. I would break it up like this. I'd have 2 rectangles and a semicircle and a little triangle there. And then you're going to have the little semicircle here and the little triangle here. Those values above the x-axis are positive. The values below the x-axis are negative. So some of these are easy to find. That is 2. This is 4. This is 1/2. The semicircle, how do we find the area of a circle? Pi r squared. What's the radius of that circle? 2. So pi 2 squared, which gives us 4 pi, but it's only half of the circle, so we need to divide it by 2. So we'll get this part right here is 2 pi. And then over here, for this circle, pi times the radius squared. What's the radius of this circle? Just 1, but divide it by 2. So that's going to give you pi over 2. And then this is a triangle, so that's 1/2 base, which is 2, times height, which is 1. We're just going to get 1 for that. So to put all of that together, we've got 2 plus 4 plus 2 pi plus 1/2. And then we'll have minus pi over 2 and minus 1. So I'd put all these whole numbers together, the 2, 4, and the -1. That is going to give you a 5. I'm going to worry about that 1/2 here in a second. And then I've got plus 2 pi minus pi over 2. Since we've got fractions here, we need common denominators. You can look at your answer choices. Like if it was free response, you could stop. You don't have to simplify this. But we can see we got fractions. So I'm going to put this over 1 and this over 1, which means you need to multiply by 2 on top and bottom here, and by 2 on top and bottom here. So we're going to have 10 over 2 plus 1/2. That's going to give me 11 over 2. And then I'm going to have 4 pi over 2 minus 1 pi over 2. And that is going to give me 3 pi over 2. And answer choice B is the one that matches that. Everybody okay here? All right, this one is a little bit tricky. It's got a lot going on. I know that the integral from -1 to 3 of 2g of x plus 4 is 22. I also know the integral from 10 to -1 of g of x is 12. And I know the integral from 3 to 10 is g of x. Or no, I'm trying to find the integral from 3 to 10. So, for this, I know the value of this is 22. But I'm asked for the integral from 3 to 10. And this is like pretty complicated. Now, if they had given me the integral from -1 to 3, that would be helpful, right? First of all, this is a backwards integral. I don't like that that is a backwards integral. So I am going to flip that around. The integral from -1 to 10 of g of x dx, what would that be? -12, right? So I know from -1 to 10 I get -12. So if I had, like, I need the integral from -1 to 3 of g of x dx plus the integral from 3 to 10 of g of x dx is going to equal the integral from -1 to 10 of g of x dx, right? And then this is what I'm trying to find. I need to find this. And I know that this value right here equals -12. So if I could find the integral from -1 to 3 of g of x dx, then I could solve this very easily, right? So that's where this comes in. So what we want to do is we want to break this down. Okay, so this can be the integral from -1 to 3 of 2g of x dx plus the integral from -1 to 3 of 4 dx. And what can I do with this 2 right here? I can just pull it out front. So I've got 2 integral from -1 to 3 g of x dx. Now this is good because now I got an integral from -1 to 3 of g of x by itself, sort of, right there, right? Now the integral from -1 to 3 of 4, what's that going to be? It's a constant. Remember, think about what that graph would look like for a constant. It is a horizontal line at x equals 4. Oh, I should have made my graph a little. I'm gonna put here. This is my x-axis now. Make that the x-axis. And we are going from -1 right here over to +3. What's the height of that rectangle? That height from here to here is 4. What's the width of that rectangle? Also 4, because I'm going from -1 to 3. So that area right there is going to be 16. Or another way you can write it is 4 times 3 minus -1. Like that. Now, all of this equals 22. So what we can do is we can treat this just like this is a variable, and we can solve for it. So if we subtract 16 from both sides, we got 2 integral from -1 to 3 g of x dx is going to equal 6. And then, again, we're just trying to get this right here by itself. So we could divide by 2. And so this integral that we just found from -1 to 3 of g of x dx has to equal 3. So what we've got over here, that's 3, is 3 plus the integral from 3 to 10 of g of x dx equals -12. And what is the last thing I've got to do to get that integral that I'm looking for by itself? Just subtract that 3. And so the integral from 3 to 10 of g of x dx is going to be -15, which is b. This is related to the problem we did like 2 examples ago. It's a lot harder though, right? You've got to kind of work with this equation to find the pieces that you need over here. I think this is a pretty tough problem, without really requiring any significantly tough math, right? We're just adding, subtracting, like nothing got too crazy on that part, but the logic is tough. All right, let's see where. Okay, we're going to. This is what a free response might look for this. So there's some other parts they might ask you that we don't know how to do yet, but for what we're going to see here, this is what a free response might look like for this. So figure to the left shows the graph of the continuous function f. The regions A, B, C, D, and E have areas 2, 14, 10, 27, and 4. So I'm going to label those on my picture here. I've got, this is 2, 14, 10, 27, and 4. And then they give us this integral defined function. And A says, is there a value of x from -5 to -1 such that g of x equals 0? Justify your answer. Okay. What does that sound like we should be doing if it's saying, is there a value that is equal to this? It's one of those theorems that we've used lots of times. Close. It's not going to be that one. It's the other one. Intermediate value theorem is the one that we're going to use here. We're not using mean value because we're not talking about like a derivative. Derivatives are with mean value. So intermediate value theorem, we just got to say like, well, g of -5 is this. G of -1 is this. Oh, we got to cross 0 at some point, right? So we would start off, since f is continuous, G is also continuous. Then we need to find G of negative 5 and G of negative 1. So G of negative 5 would be, we're taking this equation, 8 plus the integral from negative 5 to that x right there, we replace it with negative 5 of f of t dt. What is the integral from negative 5 to negative 5 of f of t dt? It's 0. We don't even have to think about it. It's 0 because if the limits are the same, you get 0. So we'll get 8 plus 0, which just gives us 8 right here. All right. Then we need to find G of negative 1. So we've got 8 plus the integral from negative 5 to, we replace that x right there with a negative 1, f of t dt. So that's going to be 8. And then what is the area under the curve from negative 5 to negative 1 of f of t dt? Nope. That'd be from negative 1 to 5. We want negative 5 to positive 1. Negative 10, since that's below the x-axis. They're always going to give you the area in positives because area is positive. But when we're doing integrals, any area below the x-axis counts as a negative. So we get negative 2. So if we go from 8 down to negative 2, do we have to cross 0? Yes. So we would say since, I'm going to do G of negative 1, which equals negative 2, is less than 0, less than 8, which is equal to G of negative 5. Sorry, it's going crazy here. By the intermediate value theorem. There is value. Of x for negative 5 less than or equal to x less than or equal to 1, such that g of x equals 0. Okay, this is a question you already knew how to do. They've thrown the integral defined function in there. So they're tested not only do you know how to do intermediate value theorem, but also do you know how to evaluate this integral defined function. So they kind of include two things there. The next one asks for absolute minimum. We're not going to have total enough time to do all of this, but you would look at critical points, right? Because if g of x equals 8 plus the integral from negative 5 to x of f of t dt. What does g prime of x equal? What's the derivative of 8? 0. It goes away. What's the derivative of this integral? F of x. So g prime of x just equals f of x. And so your critical points would be anywhere that f of x equals 0. That is going to be at x equals negative 11, x equals negative 9, x equals negative 5, x equals negative 1, and x equals 5. Which one of these could be a minimum? Could I have a minimum like at negative 5 right here? My graph of f switches from positive to negative. That tells me I have a relative maximum, right? Can a relative maximum be an absolute minimum? No. So you would want to check g of negative 9 you need to check G of -1. And then that would really be it. You need to check your endpoints on that. You increase here, so that wouldn't make sense. You need to check G of -11. I don't think so. I think it would just be those two. Or you could check every single one of them. It's just going to take a while for that. We don't have time to do that, but sorry. Let me give you guys.
You gave it out.
Oh, I gave you. You've already got your worksheet. I will give you 3 of them that you can skip on that. It's got like 19 questions. It seems like a lot, but some of them should be kind of short. Only a part. Only a part. So like on the last 2, they have like a part A, B, and C. So if you're wanting to skip a whole one of those, then that would be like your 3 questions for that.